core and insulation electric stress. The setup is simple. We have a turbine generator. The core is grounded. There is a conductor placed in the slot. Conductor is connected to the mains, so the conductor has high electric potential, and in the place where the conductor comes out of the slot, the electric field gradient and the electric field stress in the insulation are high. To grade the electric field, the semiconducting tape or paint is applied. Our task is to calculate the electric field stress distribution. Okay, let's start QuickField now. In QuickField, I create new problem. Slot. Next. Problem type is AC conduction. Frequency is 50 Hz. Every simulated device is a frequency is 50 Hz. Every simulated device is a three-dimensional object. I'm going to simulate only a single cross-section, so the model class is plane parallel and length you need some millimeters. Finish. On the left you can see the problem pane, and here on the right is the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD DXF file. I already have the model prepared in the card, so I will import it. Here you can see a part of the stator core. Let's zoom in. Here you can recognize this is the tooth, and here is the slot with the conductor. In fact, I do not need such large model. I need only this part to calculate the electric field stress in this area. So I'm going to limit the simulation domain. Switch to insert mode, draw the line here, and draw the line here and here and here. Okay. Now switch to select objects mode, select and remove unnecessary parts. I see the model features the symmetry. Let's remove the bottom part as well. Draw the line here and remove this. Now let's assign labels. Switch to select objects mode, click to select. This is the air. Type in the label name here. This is the conductor. In fact, there is no electric field inside the conductor, so there is no need to assign label to the conductor body. Instead, I'm going to assign label to the conductor surface. Click the edge and assign label high voltage. The same is true for the stator. I do not assign label to the stator body. Instead, I'm going to assign label to the stator surfaces. Click to select. This is the stator, and the stator is grounded. Now let's assign labels to blocks. Zoom in. This is the main insulation of the conductor. This is the conducting armor tape. So again, I do not assign label to the block. Instead, I assign label to the edges. Now let's zoom in. This is the armor tape. The armor tape has zero electric potential, and in this place where the armor tape is removed, the electric field stress in the insulation might be high, so the stress grading tape is applied. This is the stress grading. It's a semiconducting material. Now let's provide physical properties for these labels. Double-click the label in a tree. Electric permittivity of the air is 1. For the insulation, I specify electric permittivity of the insulation, which is 3. For the stress grading, electric permittivity is 4, and it's a semiconducting material, so here I specify electrical conductivity, which is 2 microsiemens per meter. Okay. Armor tape. Conducting armor tape has 0 electric potential. Stator core has 0 electric potential. And the conductor surface has electric potential of 15 kilovolts. In fact, this is the root mean square value. In QuickField, you should specify the magnitude of the sinusoidal wave, which is root mean square value times square root of 2. Okay. Now the geometry model and material properties are ready. Before I can run the analysis, I should build the fine element mesh. Just press this button and the mesh will be generated. Now save all problem files and solve the problem. The problem has been solved. Let's take a look at the results. Here you can see the electric field stress distribution. Let's zoom in. You see there is the high electric field stress in the insulation, and in the place where the conducting armor tape is removed, the electric field stress is high. You may note that the field lines are not smooth curves here. That's because of insufficient fine element mesh density. QuickField allows you to automatically adjust the fine element mesh to get more accurate results. Press Solve and Refine. The mesh will be automatically refined. Now let's take a look at the results again. You see we have new maximum value of the electric field stress. Again, I zoom in and find the place where the conducting tape ends. There is also an option to manually adjust the mesh density. Let's open the geometry model and find the place where we are interested to calculate the electric field stress. Here, I select this edge and specify manual value of spacing. 0.1 millimeter. No, that's too large. 0.01 millimeter. That would be fine. Let's build the fine element mesh and run the analysis again. Again, let's zoom in. Now you see that these boundaries between the color zones are more or less smooth curves as it should be. Okay, my task is to find the electric field stress in the insulation. So let's use the contour tool. I will switch off the color map electric field stress, so you will be able to see better what I'm going to do. I'm going to select the insulation surface. Use the contour tool. Click to select. You see this green line. Click to select this edge. And I will add this edge too. Now I have the contour line along the insulation surface. Let's take a look at the electric field stress distribution on the XY plot. We can see that this spike is high and this spike is relatively low. The exact values you can see in the table. This one is at 110 millimeters and this one at 180 millimeters. Let's see. Let's adjust the table view. I need only the coordinate and the electric field stress. Perhaps we can get better results if we use stress grading with some other value of electrical conductivity. For example, 5. Let's solve the problem again. Again, I'm going to build the contour along the insulation surface. Click to select this edge, and this edge. Open the XY plot. Now you see this spike becomes a bit lower and this spike becomes higher. Let's check the exact values. Open the table, columns, distance, and the electric field strength. And the row stabilizing step is 10 millimeters. Okay, this spike was 9.5 kilovolts per millimeter. Now it is 8.7. This spike was 1.8. Now it is 5.6 kilovolts per millimeter. This way, using the simulation with QuickField, you can find out what properties of the stress grading are required to reduce the electric field stress in insulation. If you search for the core and insulation electric stress on our website, you will find the example page. Here you can read about problem setup, browse the solution section, look at the resulting pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.